Okay, so up to the last class, do you have any doubt? Anyone? Any confusion up to the last class? I hope no. Okay, so in the last class, what we did, we have solved some problems with using the instantaneous center of velocity analysis. Okay, there we have utilized that instantaneous center method, that concept of instantaneous center, and that particular method we have utilized to find out the velocity of some points on a particular mechanism. Okay, so in that case, if you recall, so what are the different steps involved? Do you remember? So first thing, you have to draw the configuration diagram of the given mechanism as per some suitable scale. Okay. Next, what we have to do? So if it is instantaneous center method we are talking about, then we must know how many instantaneous centers are there for that particular mechanism. For that, we had this particular equation, that is number of instantaneous center. It is given by n whole into n minus 1 divided by 2. So those n's are nothing but the number of links. So depending on whatever is the type of mechanism, so you should be able to number the link, find out the number of links, okay, and utilize this particular small equation and find out how many instantaneous centers are there. Then after that, what was our task? Our task was to name them. Okay, so which are the instantaneous centers? Okay, so suppose in between link 1 and 2, okay, we have got instantaneous center I suffix 1 2, that is nothing but instantaneous center between link 1 and 2. So that way, whatever is the different instantaneous centers, the nomenclature you have to find out. Okay, and after that, your task will be to, you should be able to locate all those instantaneous centers. And for locating the instantaneous centers, we have got different methods. Different methods means some standards are there. Like if you are talking about, suppose your uh, pin join, okay, two links are being joined by a pin join or a hinge join. Then where is the location of the instantaneous center? Who can tell me? So the location of the instantaneous center in case of two links which are being joined by pin or hinges, nothing but at the center of the pin itself. Okay, so that way you can look at similarly for sliding pair. Okay, so it's nothing but it remains at infinity, but in a direction perpendicular to the direction of motion. Okay, so in the case of our slider crane mechanism, it was the line of perpendicular to the line of stroke direction at infinity. Okay, so that way you have considered. And later on, for finding out some other neither permanent nor fixed type instantaneous centers, we use the Kennedy's theorem of three centers, which says that three links or three bodies, if they have got plane motion between them, so the three instantaneous center between them, they remain on the same straight line. So that logic also we utilize, we find the, and we locate all the instantaneous centers. And after that, we utilize the concept of the proportionate distance of that particular point from a from the instantaneous center to find out the velocity. Okay, that we have completed. So now today, up to this much, do you have any confusion, anyone? If no, also let me know. If there is no confusion, then we can move ahead. And today we will study about the acceleration analysis. Okay, what are the different components of acceleration that is there, how to draw the acceleration diagram. Okay, so that kind of thing we are going to discuss today for simple mechanisms. Okay, let me know up to this much. Do you have any doubt? Clear, sir. Okay, so clear. Okay, thank you. So now today we will be going for the acceleration. So now we know what is acceleration. It's nothing but the rate of change of velocity. Okay, with respect to time. That is rate of change we are talking. Then it is nothing but the first derivative with respect to time. Okay, and as we already know, it's a kind of vector quantity. That means vector means both magnitude as well as direction will be required. Okay, so as to completely specify that particular quantity. Okay, only if you know about that acceleration in terms of its magnitude, then also it is not enough. Only if you know about its direction, then also it's not complete. Okay, so we have to have both magnitude as well as direction. Okay, so now there will be situation when will be basically, as we are talking about acceleration or velocity and acceleration analysis for mechanism. So with respect to links, we will be discussing. Okay, So now let's consider 2 points A and B, which is on a rigid link. Okay, so A and B. Suppose in this figure, if you look at, so we'll see 2 points. Okay, so point A and point point B. Let's consider there. Okay, and point B, it's moving relative to A with an angular velocity and angular acceleration respectively, and omega radian per second and alpha radian per second square respectively. Okay, that is for point B, movement of point B with respect to A. Okay, and as shown here. Okay, so suppose this is the omega angular velocity of it, and this is the acceleration alpha. Okay, so omega we denote for angular velocity, and with alpha we denote angular acceleration. Okay, and for omega it's angular velocity. What is the unit? It is radian per second. For angular acceleration, it is radian per second square. Okay, so now velocity of point B with respect to A, or the relative velocity of point B with respect to A, how we can write V of B A, velocity of B with respect to A. So if you can recall, so this velocity is nothing but it's a perpendicular to the link itself. Okay, so this way velocity of B with respect to A will be there. Okay, and we already know how we can compute it. VB equal to omega into AB. Okay, that is just like the V equal to R omega. So here R becomes the link length, omega is nothing but the angle. Okay, now let's come to the acceleration. Now, this particular velocity of a particle, now if it changes, okay, so acceleration we know it's nothing but the rate of change of velocity with respect to time. Now, this velocity of a particle, if it changes both in magnitude, okay, then it has got two component of acceleration. So see, as it's a vector quantity, so what may happen, even if it changes in magnitude, then also there will be some component of acceleration. Or if it is changes only in direction, then also there is change. Okay, some rate of change. Okay, so that's it. Now we must know what are the different two different acceleration components which are there. So first thing, there is one component known as the centripetal or radial component of acceleration, and this component of acceleration is actually perpendicular to the velocity of the particle at that particular given instant. Okay, so and the magnitude of that particular component is given by, so we are using F for denoting your acceleration, and F superscript R for radial. Okay, and it is of B with respect to A. Okay, you can also use A. Okay, suffix R, radial component of acceleration. But why we are not using this A, B, A? Okay, because in most of the cases, while drawing the figures, there also will encounter the points like A, B, etc. Okay, so to not get confused, you can denote acceleration is smaller. Okay, so the superscript R represents the radial acceleration component. So it is given by omega square into B. That is the angular velocity square into the length of this particular B. Okay, so that will give you the magnitude of radial component of acceleration of B with respect to. And now the direction of it. Okay, so it is what? It is perpendicular to velocity means what? If this is the velocity, okay, so that means perpendicular to it, this particular direction will be. And for B to A, we have to denote from the cursor will be from B to A. Okay, so the direction is from B to A, and definitely as this is the direction for radial component, magnitude is given by omega square into this particular length BA, and you can say it is along the link, or you can say it is perpendicular to the velocity. Okay, that is the radial component, or also known as the centripetal component of acceleration. Next, we have got another component that is known as the tangential component of acceleration. Now, this tangential component, it is parallel to the velocity of the particle at that given instant. Okay, so parallel to that given instant means what? So once again, F. Okay, for tangential, we denote it with superscript T for tangential, and BA means acceleration, tangential acceleration of acceleration component of B with to A. Okay, Now it is given by magnitude is given by alpha into the length. Okay, so this is the magnitude of acceleration, tangential component of acceleration. Okay, and direction, so it is parallel to the velocity. Okay, or perpendicular to the length. So this way, this is the tangential component. Okay, understood both the components. Now the total acceleration of point B with respect to A is nothing but the factor summation of both radial acceleration and the tangential acceleration. Okay, so two components of acceleration that we have got, that is the one is the radial component, also known as the centripetal component of acceleration. Next one is the tangential component of acceleration, and the total acceleration is nothing but the factor summation of both of them. That means if we want to have that only f of b, okay, total acceleration of b with respect to a, not the tangential component, nor the radial component. Okay, the total one, if we want, it is nothing but the vector summation of both tangential and radial component. Okay, radial component of acceleration plus the vector summation. Okay, plus the tangential component of acceleration. That means if it is a vector summation, and if we want to go for graphical method, how we can obtain? So we can draw previously what we have seen along this direction. We have got the radial component, right? And along this direction we have got the tangential component. Okay, so what we can do, we can start from here. So let's this point be b dash. Okay, and up to x we are drawing suppose the radial component of acceleration. Okay, so in magnitude as well as in direction this way. Okay, and now this component, tangential component, we are replacing up to this mass in magnitude as well as in direction. We are drawing here. Okay, that is the tangential component. And if you go for triangle law of vector distance, so this way, this third line, third side along this direction will give you the total acceleration component. Okay, so that's to remember. Okay, after this much, is it okay? Let me know the two components of acceleration, in which direction they are acting, how to get the total acceleration. That I believe all of you have understood. Let me know. Yes, yes or no? Let me know, someone, please. You can unmute. Okay, okay, thank you.
Yes, sir.
Okay, thank you. Now, this kind of diagram is known as the where we are showing the total acceleration of a particular link, or ultimately this can be extended to for any kind of mechanism. So this kind of diagram is known as the acceleration diagram. So here once again it's a kind of graphical method. So drawing them in proper scale is important. How to find out the magnitude and direction? Magnitude for in case of your radial component, it is given by omega square into link length. Okay, similarly for tangential component of acceleration, it is alpha into the link length. Okay, so now alpha means what is what we denote with alpha in case of this movement? It is angular, what, omega is angular velocity, alpha is angular acceleration, right? That means rate of change of angular velocity. At what rate the angular velocity is changing, that gives you this alpha, right? So now if there is no change in omega, that is omega is constant, then what will happen? Will there be any alpha? If omega is constant, there will not be any change in this d omega dt will not give you any value because it's a constant, omega is constant. Okay, so in that particular case tangential alpha will become 0 and tangential component automatically will become 0. So that means tangential component will not exist, tangential component of acceleration will not exist if there is constant angular velocity. Omega is constant. Understood? So that is the thing. So now the same thing has been drawn here. Okay, this is the total acceleration vector summation. Okay, how to draw the acceleration diagram already we have discussed. Okay, first as per suitable scale we are drawing that particular radial component. Okay, then from that point, okay, actually considering alpha is known, that we are taking that tangential component. Okay, we are drawing this. This is the figure we are talking about. Okay, and after that the third side, okay, it gives you the total acceleration. Now you can see here one angle, this angle is shown as beta. Okay, so now this total acceleration, this is the total acceleration line. Okay, it is making an angle beta with the radial component, right? So when you join a dash to b dash, that to get the total acceleration, okay, of p with respect to a. Okay, so that is nothing but the acceleration image of the link AB. Okay, so now this acceleration of P relative to A is inclined to AB at an angle beta. And how to get it? From this particular diagram, all of you can very easily say this is a right angle triangle. So here we have got the tangential component. This one is nothing but the radial component. Okay, so if I take tan of this angle beta, how to get? So tan beta is nothing but the tangential component of acceleration divided by radial component of acceleration. Tangential component, how to get? It's nothing but its magnitude is alpha into AB, radial component omega square into AB. So after that, what will remain? AB will get cancelled. Tan of beta is alpha by omega square. Okay, that means this angle beta, it only depends on the value of angular acceleration and angular velocity of the body, and it is independent of the location of both the points A and B. So AB, it gets cancelled. So location of the point, it is independent of the location, but it only depends on what is the angular acceleration and what is the angular velocity for it. Okay, let me know whether you have understood or not. I hope you have understood. Okay, so now we'll see how to draw the acceleration for two given points. Okay, up to this much, is it okay? Let me know. Then I'll move ahead. Yes or no?
Yes, sir.
Okay, thank you. Now we'll consider a situation where acceleration of two given points is and it is given. Suppose FA, FB it is given. So the magnitude of angular acceleration that you have to find out. Okay. So now let's consider this as the link AB, and in this direction, okay, it is moving with an angular velocity this. Okay, omega. Now let's for point A. So FA, F suffix A, be the acceleration, and direction is this direction. Okay, F suffix A, acceleration of point A. Next, for point B, let's consider, suppose this way. Don't consider this direction as per this particular figure. This direction is wrong. So let's consider as if it is here in this direction. Okay, so this way, suppose we have got the magnitude. Okay, so the acceleration F suffix A of point A is known in magnitude as well as direction. Okay, and FP, that is F, it is acceleration only in direction. Okay, this way only it is there. Okay, we know like that. And what we need to find out, the magnitude of alpha of AB, that is the angular acceleration of link AB. It has to be determined, and we are going to go for graphical method. Now, how to do it? So for that, what we will do, this is the link AB that we have, right? So FA is here in this direction, magnitude as well as direction both are known. FB is like this, okay, for point B. Now we'll start with any point O. Let's consider this point as O, and we are going to draw a line which will represent f of a in magnitude as well as direction. So we are going to, let's consider as per whatever is the scale you have considered, the magnitude and direction, it is already known as I have as per the question. Okay, so we are going to draw a line OA. So this is for point A, and here we will denote with small a. Okay, and what is this line? It is nothing but the value of FA in magnitude as well as in direction. Okay, so O is drawn. Now from A, from this point A, we are going to draw another line which will represent the radial component of B with respect to A. Okay, we are going to draw AX. Okay, and how much we are going to draw? We are going to draw AX, that is nothing but the radial component we are going to draw. So this AX, it will be the radial component. We know that there are two components. One is the radial component, another will be the tangential component. And total, how to get the total value? Okay, actually, if we know about radial component and tangential component both, okay, in magnitude and direction, then total acceleration, okay, it can be obtained by the factorization of these two. So now here, what we'll do? Actually, the total acceleration we don't know, that we want to find out. So for doing so, what we are going to do? If possible, we are going to find out the radial component and tangential component. Then we'll do the vector addition of them, and it is going to give us the total one. Okay, that is what is we are going to do. So radial component. Now we know that, see, the omega is already given, right? And the link length AB also is known. So from there, very easily we can get the radial component for acceleration, right? And how to get it? As per our previous expression, omega square into AB, that is going to give you the magnitude of it. Yes. And what will be the direction for radial component? Radial component is along the link, right? So parallel to this link, okay, we are going to draw this AX. Magnitude will be this much, omega square into AB, and direction will be parallel to AB. So this one. Let, as per the whatever is the scale. So this one is the radial component. Okay. Next, this is X. Now next from X, what we will draw? We are going to draw a perpendicular line, and that we know that it is going to denote the direction of, along this direction actually, the tangential component we are going to draw, and on that somewhere the point B will be there, because we are talking about this acceleration of B with respect to A. Okay, so now from X, what we will draw? We are going to draw a line which is perpendicular to AX. Ultimately, it is perpendicular to the link itself. Okay, so that is the tangential direction that we have already discussed. Okay, tangential component direction is perpendicular to the link. Radial component direction is along the link. Okay, so now from here we'll draw like this. Okay, right now I know that somewhere we have got the B here, but I exactly don't know where is the point exactly. Okay, B point from this direction. Now I have to locate properly the B point also. Okay, up to this much, it's clear. It will contain B. Okay, because AB is the link. Okay, it will somewhere contain B, but exactly where the B point is there right now I don't know. Up to this much, I believe it's clear.
Yes, sir.
Okay, thank you. Next, if you go back to the previous diagram, once again, what was given? So till now, whatever we have drawn considering that FA, okay, and the derivative from there. Also, in the question, we knew about FB in direction. We didn't know about its exactly magnitude and all, okay, but we know that this way FB is there. So from O, we are going to draw a line which is going to represent FB in that same direction. Okay, so parallel to this line, we are going to draw a line. Okay, that is FB. Okay, and now it is going to intersect the previous line, the tangential component line. Okay, this was the tangential component line. Okay, at some point, and that point is nothing but the B point. It will contain the B point. Previously, we didn't know that where is the exact location of this point. We knew that it is somewhere here. Also, this is the direction for the f of B. That means here only B point will be there at the intersecting point. And now let's join that O to B. Okay, that is done. And now we'll join this point B with point A, and that is going to give us f of BA. And this particular vector, it is vector AB, it represents f of BA. Okay, so the drawing is done. Now our task will be to, we need to know the values, right? So for that, what we can do, we are going to measure it. We are going to measure by using scale. So Bx and all, everything can be measured. Bx can be measured. Ax already has been measured. Okay, as per measurement only, we have drawn Ax. We have previously drawn in direction only. Now we have located the point B. That means this pass can be now measured. Bx. Now measured is Bx value and convert. And that is nothing but Bx, that distance if you measure, that is nothing but the tangential component, right? So f of t p a. Okay, and from there, if you want to have the, see, if you recall the tangential component, okay, this is given in magnitude as alpha ab into what, into the link length ab, right? So now if you need this alpha value, okay, so it is nothing but bx by ab. Okay, so this is nothing but bx by ab. So bx is directly, just now we have measured and converted the value and obtained the value, and ab is already known, that is the link length. So from there, now from this part, taking the help of this particular figure, you can obtain alpha of ab, and that completes our problem. Okay, now it is known. From the figure, we have measured this value Vx. Okay, that is nothing but the tangential component. Tangential component is given by alpha into that link length AB. Okay, so from there, alpha can be obtained. Okay, and that was our task, to find out the alpha value, angular acceleration. Okay, so let me know whether you have understood on. So this class, all of you have understood.
Yes, sir.
Okay, and there's also I have I think all of you have understood. Okay, so these things once you systematically go na, so then it becomes easy. Otherwise, later on, if you directly see some figures, sometimes radial component is drawn, sometimes tangential component is drawn, and you may get confused that way. If you don't know, suppose two components we have got, the total can be obtained by the factor addition of radial component and a tangential component. Those things, if you don't know, later on you may get confused. Okay, but if you systematically go that go, and if you know, suppose radial component, what is the direction, it's along the link. Okay, then tangential component, it's nothing but the perpendicular to the link. Okay, that is the direction. Similarly, addition of these two, factor addition of these two is going to give you the total acceleration. All those things, okay, you must remember. Okay, and then the rest will be easy. So there are two when the velocity changes in magnitude as well as direction. So two component of acceleration that we get. One is the radial component, also known as the centripetal component of acceleration. Next one is the tangential component. Okay, so these are the main basic things. And using this, we have seen how to draw the acceleration diagram from link or to link and all. Okay, and same thing can be this thing can be extended for some simple mechanisms like the forward mechanism, slide diagram mechanism, etc. Okay, so next, similarly, there is a concept of acceleration center of a link. Okay, so by this time, whatever we have discussed, you just go through. If you have understood that thing, and if you just go through it, okay. Then this thing acceleration center, what is it called? Okay, so it will be easy. And this concept of acceleration center is very useful for determining the acceleration force, accelerating forces in different mechanisms. Okay, basically once again there will be that just like in the velocity diagram while drawing velocity diagram using the instantaneous sensors now. Okay, so there also we have seen basically it's some proportional relationship has been maintained. So here also similar is the case that is happening here. Okay, so up to this much I believe all of you have understood the basic concepts of it, and based on this anything I believe all of you will be able to, right? This is the basic main thing, how to draw. Okay, same thing can be extended for any number of links. Yes, now all of you have got, I believe all of you have got the confidence. All of you have got the confidence or not? That means velocity, acceleration, diagram, this kind of things I'll be able to draw. These are vector methods. Okay, so vector methods as well as these graphical methods. Okay, so proper scale, considering proper scale is very important. That thing has to be maintained, and rest will follow. Maybe in next class some small problems we'll see. Okay, how to draw the uh, acceleration diagram. So now the thing is, for why we have studied velocity diagram previously, because the thing, so while going for the acceleration diagram drawing, okay, then also you'll see, so as you have seen that what component of tangential component is your parallel to the velocity itself, okay, or ultimately perpendicular to the link. So later on you'll see that velocity, while you're going for acceleration going to go for acceleration analysis by graphical method, so these diagrams you have to draw. So in that particular case, the first step will be to draw the or the construction of the velocity diagram. So based on the velocity diagram, in the next stage, you are going to draw the acceleration diagram. So that's why both the concepts are important. Okay. I hope all of you understood. So now, apart from these two concepts, okay, there is another acceleration component which is very important, okay, and it has got various effects, okay, in practice, even in your daily life, okay, like this particular Coriolis acceleration component, it's a very important one, okay, and it is, see, the total component of a rigid link, okay, on the same rigid link, okay, we have seen that the total acceleration on a point with respect to another point on the same rigid link, it's nothing but the vector summation of its radial and tangential acceleration. Okay, that thing we have discussed. We know already. We know it, but it is true only if the distance between both the points, whatever A point and B point we have discussed now, between link, okay, only if it remains fixed, then only this is. Now, there may be some situation in some mechanisms or in some real life cases, there may be some situation when the distance between the 2 points is not fixed. If not fixed means, suppose one point is fixed, or maybe now this point B is moving with respect to point A. That means the total distance is not fixed now. Now, in this kind of cases, what will happen? The total acceleration will have one more component of acceleration, and that is nothing but the Coriolis component of acceleration that will have. Now, this particular Coriolis component of acceleration will only exist when there is sliding as well as rotary motion of a particular point, and generally it is denoted by F suffix CC for Coriolis component, or only FC, F superscript not suffix, okay, superscript C, or sometimes FCR in short Coriolis. Okay, so now the thing is, see, we know rate of change of angular velocity is angular acceleration. Okay, and in these cases, now if whenever we are saying that the distance between 2 points is now not fixed, now that means it has to have, it is rotating also, and at the same time it is sliding. That means This acceleration component will come when there is sliding as well as rotational motion of a point. Okay. Now, can you give me an example of a standard mechanism that you have seen in different in workshop, etc. I am giving you the hint. Okay, where you have got both rotational rotary motion as well as reciprocal motion or sliding motion of a particular point. Particular point means particular link you can control. Do you recall a mechanism already we have studied this thing where you can see both sliding as well as rotational motion for a particular point. This suppose that is rotating also and having the rotational motion also, and suppose it is sliding also. I'm giving you the hint. It is uh, generally in workshop, mechanical workshop. This particular mechanism is there. This particular machine is there. On that machine, this particular mechanism is there. If you can recall, who can tell me?
Sir, planar.
Planar. Okay, planar is the next person. Okay, the separ mechanism we're talking about.
Yes,
Okay,
quick return mechanism.
yeah, the quick return mechanism also you see. So you have seen that particular slider, okay, that is there on that particular link, okay, and then slotted lever mechanism you can consider, okay. So that is there on that particular crank that is rotating also as well as in that particular case. So the slider, if you consider, that is having reciprocal motion. So in those kind of
Sir,
cases, while you are, yes,
sir, can we consider IC engine that piston cylinder arrangement as this kind of example?
a piston cylinder arrangement
Rotational and
generally
sliding.
generally piston cylinder arrangement actually in normal W engine or V shape engine, generally the rotational motion is not there. Okay, it is a constant kind of motion if you can recall. Even though the piston is able to rotate within that particular cylinder, but that motion is restricted. Only it moves up and down. That piston only if you consider that particular portion.
Sir, crank is also means rotating, no, and it is also sliding the piston. So
No, no, that's right. Those are the two different elements, right? The crank is there. Okay, next the connecting rod is working as the particular that's piston there, slider there. Okay, connecting rod along with the slider becomes the piston, connecting rod is that particular connecting rod.
oh yes, got it, sir.
Okay, so right now
Okay.
we are talking about the same point which is having good motion. Okay, so it will be in this kind of cases in crank and specific kind of mechanism. So as it is situated on the crank itself, so along with the crank that is having the rotational motion, and it has got the sliding motion on that particular. Okay, both the motions are there. So in those kind of cases, so this is one of the very important questions. Sometimes in competitive exams, sometimes in interviews, it is generally asked. Okay, in which of the following, suppose mechanism co-release component of acceleration exists. Suppose they will be giving separate mechanism, suppose slider crank mechanism or something like that. Four options. So in that case, you should know that in this kind of situation where both the motions coexist, so there the co-release component of acceleration will come into picture. Okay. So maybe about this Coriolis component as well as some problem with respect to acceleration analysis, we'll be going through in more details in the next class. So up for today, up to this much we'll stop here. So let me know whether today's discussion you have understood or not. You may let me know. I think all of you have understood, right?
Yes, sir.
Okay, so yes, even though it's not here in this syllabus, okay, some
Yes,
interesting
sir.
fact, some interesting fact about this Coriolis component. Okay, maybe most of you play video games, right? So maybe the shooting games or like that. Maybe sometimes you might have seen in some game, suppose in the sniper kind of game. Okay, you might have seen that Coriolis component has to be taken into consideration. So now in those long range shooting, that's generally made by the snipers and all. Okay, there this art movement of the art. Okay, so the sense of like actually the distance it is changing, right? Okay, so along with the rotation of the planet, so distances of different points with respect to some fixed point that is also changing. So in those cases this correlates component of acceleration that has to also be considered. Then only your a long range suit that is a sniper shot and that kind of shot can hit the target properly, along with all those other effects like wind, humidity, etc. So the correlates component also you have to take care of. Similarly, those aeroplanes, etc. Also, okay, they also like those component. This you can say this Coriolis component plays a vital role there also. Similarly, in the whenever we track the satellites from the Earth, okay, or maybe propulsion of satellites, etc., in its desired orbit, there also the Coriolis component has to be considered properly. Similarly, sometimes you might have seen maybe the hurricanes and all, snow, different hurricanes, all those different different can say that kind of things building up. Okay, those very big wheel, etc. Okay, so there also these things actually ultimately it comes into picture. Okay, so this is apart from mechanisms and all in real life in nature also these components exist. Okay, so these are beyond your syllabus, but these are some fun facts to know. Maybe some have you seen anyone who plays in video games, etc.? You might have seen. Have you heard the Coriolis component? Maybe while doing for maybe some maybe sniper games and all. Anyone recall? How many of you people play computer games and all? Computer games, video games, etc. No one.
Most
You're
of
very
us, I
good
guess,
bets.
sir.
So almost
Yeah,
everyone.
almost everyone. Then
Sir, not
have
me.
you? Not you. Okay, what do you play? Outdoor games, indoor games,
Sir, outdoor
PlayStation.
games.
Okay, that's good actually. Having physical activity that is good. Okay, and along with physical activity, there's outdoor games. Even if sometimes you play limited amount of computer games or whatever. Okay, that is also not that much harmful as per my view. Okay, playing more than enough. Okay, that is definitely harmful for both your health and mind. Okay, but sometimes nowadays all those games also, etc. Also like very you can say tech savvy means in like in the games also you can learn a lot of things, sometimes even some mechanisms, some different elements of different different working elements of suppose different things even you can learn from games also. Okay, so I hope all of you have understood today's class. So with this we'll stop here. I will be taking the attendance. I'll be calling your names. Please respond. Samim, please respond to your name calls. Okay, I'll be taking that. Samim, Vishal, you can mute yourself. Your some noise is coming.
Sorry, sir.
Samim is here. Hitesh sir,
Yes, sir.
Vishwajit,
Prince, sir.
Catherine,
Present, sir.
Tapas, Tapas. I can see Tapas. What happened to him? Jigyas,
Present, sir.
Shubham,
Present, sir.
Andreas.
Yes, sir.
Andreas is here. Andreas, why don't you
Yes.
generally like you are generally absent? What happened? You are coping up with the things or not?
So little bit.
So don't do that. Otherwise, you'll get it will be harmful for you. Okay, you study well. Okay,
Yes, sir.
Ashish,
Present, sir.
Khandip. Okay, Khandip is not there. Vishal,
Prince, sir.
Sempang. I can see Sempang. What happened, Sempang? Albiak Sina,
Yes, sir.
Dorian,
Yes, sir.
Sensing Dao,
Yes, sir.
Mario,
Present, sir.
And Norangsi.
Present, sir.
Okay, thank you everyone. Jaideep is here. Jaideep, I can see Jaideep, but what happened to him? Okay, thank you everyone for joining the class. We'll meet in the next class.